Hi, everybody. As you can see from this paper right here, this is one of your upcoming assignments. And typically students, they have a few questions on some of these problems. So what I thought I'd do was I'd either do some of these exact assigned problems or I'd do some of the even or odd problems that aren't assigned, just to give you some help and some guidance when you get to these questions on this assignment. If you want to, you might want to grab your textbook, have it handy so you can be looking off of it as we work some of these problems. All right, I'm on page 273 and number 10. I'm not going to write this problem down. Sometimes I'll write the problems down and then work them out, and sometimes I won't. But for problem number 9 and 11, which are your assigned problems, we're going to do 10 and 12, some similar ones to help you understand what you're being asked to do here. But the reason I'm not writing them down is you can see how lengthy that might be for me to do so. All right, so we're going to start with number 10, so you can go back and do 9 and 11. The directions say to write the limit as a definite integral on the interval from a to b, where c subscript I is any point in the ith subinterval. So for number 10, this is saying to us the limit as the delta, the partition, goes close to 0. This is just saying the width of every rectangle approaches 0. We want to find a definite integral that represents this limit of a Riemann sum on this interval. Well, when we go to our paper to write down the answer, I want you to think of 0 being A and 4 being B. And then to remind ourselves when we looked at and we studied the limit definition of a Riemann sum, okay, this is going to be our f of x, our function, and this is going to be our little dx, or our differential in x. So we really want to pay attention to what's happening right here in our f of x situation. So everywhere you see a c subscript I, replace those with x's. Those are our x values in an I interval. So you might want to be looking at the structure of this, and I'm going to go to what the answer is for this problem. So that limit of a Riemann sum can be represented by the definite integral from x equals 0 to x equals 4 of 6x quantity 4 minus x n quantity squared, and we'll change the delta x sub I to dx. We're done. We'll do another one of the same one. Okay, if you're looking at number 12 in your book, the partition is 1 to 3, or it says the interval down that column. So the definite integral from x equals 1 to x equals 3. And then what we have is we have 3 over c subscript I squared. So that's going to be replace c subscript I with x. We'll square it. And then the delta x sub I will be replaced with dx. So those should help you with problems 9 and 11. Okay, I wanted to look at the next group of problems, 14 through 22. We'll do a few problems in there. I know you have the odd ones, but we'll do some even ones to help you understand the assigned odd problems. Okay, the next 3 problems come from the same section. So if we're looking at problem 14, the directions say, set up a definite integral that yields the area of the region. Do not evaluate the integral. So on 14, I can see that I have the function 6 minus 3x. That's this equation drawn here. And I have this shaded region that falls below this graph to the x-axis. So when we evaluate this picture here, we see that the definite integral would go from x equals 0 to x equals 2. And then of the function 6 minus 3x with respect to x. So we're just setting up the definite integral for 14, not solving it. And we're done. Let's look at 18. So you should have your textbook close to you. You should be looking at it. For those of you guys that don't have your textbook, maybe somebody can snap a picture and send it to you. What would be a definite integral that would represent this shaded region from this curve of 4 over x squared plus 2 down to the x-axis? Well, the area is accumulated, collected from x equals -1 all the way over to x equals 1. There are limits of integration of this function with respect to x. And the next one is 22. Okay, 21 and 22 kind of change gears on us. Instead of having functions in terms of x, we have equations in terms of y, as you guys can see in these equations. So what that means when you're looking at a picture of, like, say, 22, that this is the equation quantity y minus 2 squared graphed this way, but the shading is going to go to the y-axis. Okay, kind of like 21, you can really see the shadings being pulled to the y-axis as opposed to being pulled down to the x-axis. So this actually is going to be an integral with respect to y, not with respect to x. So the definite integral that would represent this shaded region is going to have y limits of integration. So I see the lowest y value is y equals 0, and then I quit collecting the shaded region up to a y value of 2. So this is going to be the definite integral from y equals 0 up to y equals 2 of this equation with respect to y. It's dy here. All right, now we're going to go to the next section of problems. And let's see what they want us to do. We'll do a couple in this section. That would be these problems down here. Now we're going to do just the opposite of what we just did. We're going to sketch a region whose area is given by the definite integral, and then we're going to use a geometric formula to evaluate the integral. So we're going to actually produce one of these types of graphs right here based on the equation, but then we're going to actually have a geometric shape where there's a known geometric formula that we can actually find the value of the shaded region. So I'm going to do 24, and I will write this problem down because it's not too bad. Okay, we're supposed to sketch a region whose area is given by this definite integral. This is our function, f of x. So I'm going to come over here, and I'm going to actually draw what f of x equals 6 looks like. Well, if I say this is 6, well, this just graphs as a horizontal line. So what part of this horizontal line do I want to consider from x equals -4 to x equals 6? This is just a rough sketch. So I'm going to draw like in a vertical line here at x equals -4 and x equals 6. So from the function f of x equals 6 down to the x-axis between x equals -4 and x equals 6, the geometric shape that I have is a rectangle. That area is base times height. So the value of this integral can be found exactly by using that area formula for a rectangle. So the value of that integral is the base. Well, counting down here along the x-axis, the difference between these two x's, 6 minus -4, the base is 10 and the height is 6. So the value of this integral is 60. All right, next problem. Let's sketch a graph of x over 4. Well, I like to think of x over 4 as 1/4 x. And I'm going to sketch that graph from x equals 0 to x equals 8. So this is a linear function with a slope of 1/4. So I'm just going to plug in x equals 0, my lower limit, into this function, and I'm going to get 0. Then I'm going to take the upper limit, 8, and plug it in for x in the function, and I'm going to get 2. So if I went over to x equals 8, then I would go up to x equals 2. So these are 2 points that I found on this function. When I connect, I've got a part of that line, that linear function, 1/4 x. I don't need anything beyond x equals 0 and x equals 8, so I might draw in a vertical line here. So from x equals 0 to x equals 8, we're talking about finding the area in that region, which happens to be a right triangle. So we have to go ahead and find the area using that known formula. Base times height divided by 2. The base is 8, the height is 2, and I divide by 2. So the value of this integral, which represents the area in that shaded region, is going to be 8. Okay, I'm going to actually do 29, which is one of your assigned problems. So you might want to look at, let's see if I can get that on here, 29 is this definite integral right here. Then we're also going to do 31 as well. Those will be 2 problems you won't have to do on the assignment because we did them together. I didn't write down the parentheses. I didn't feel like it was necessary. It's funny how many students kind of forget how to graph this. Well, we can graph this without a calculator, but if you're at home and you need a calculator, pick up your calculator, type that into Y1 and graph it. You might want to do a window setting. Go to your window and do x min -1 and x max 1. But let's just think about revisiting transformations. This is the absolute value function, that V-shaped graph. It's been reflected. So when we reflect the absolute value of x because of the negative here, we might get something like this right here, this V-shaped. But then this tells us to translate that reflection up 1. So 0, 1, and then I would create my V-shaped graph. Again, you can use your calculator to assist you in graphing, but hopefully you might remember, some transformations. Okay, I know this y-intercept is -1, and I know this, x-intercept is -1, and this x-intercept is 1. So we're talking about the graph of this function to the x-axis from x equals -1 to x equals 1. So we're talking about this region. It's a triangle. We'll use the triangle formula. The base covers a distance of 2. The height is 1. And then we divide by 2. So the value of that integral is going to be 1. Okay, 31. It's rare that any student remembers what this would look like when graphed, and I don't blame them. Pick up your calculator, type it into Y1. Window setting, x min -7, x max 7. What you're going to see is what looks to be a semicircle. Now the calculator has limitations, so it might not look like that semicircle comes all the way down to -7, but it does. So this is a semicircle whose radius is 7. So I'm going to go left 7, right 7, and I'm going to go up what I think is about 7. And I'm going to draw in this semicircle. Again, your calculator won't probably take this semicircle all the way to the x-axis, but it should go there. The calculator just doesn't like to draw anything that might look vertical, since it's a function calculator and a vertical line's not a function. All right, so what geometric shape do we have? Well, we have a semicircle. The area for a circle is pi r squared. So let's go ahead and divide it by 2. The radius is 7. I'll leave my answer in terms of pi. No need for a calculator. This is 49/2 pi. Or write it as 49 pi divided by 2. All right, hopefully those examples will help you with the problems assigned in those sections. Okay, moving on to the next section. Students oftentimes get confused here. Okay, it says evaluate the integral using the following values. So this is given information, and this is given information. These three values of these different integrals are going to be what we're going to use to answer the questions given in this section right here. So notice that one of the givens is the definite integral from x equals 2 to x equals 4 of x cubed with respect to x is equal to 60. Likewise, the definite integral from x equals 2 to x equals 4 of this other function x with respect to x is 6. And then the definite integral from x equals 2 to x equals 4 of, think of this as being a 1 in here. Okay, a horizontal line at 1 is equal to 2. So we're going to use these given pieces of information to help us solve these problems down here by using the properties of definite integrals. So you watched a video about what's allowed, what's not allowed, what you can do, what you can't do with definite integrals. Okay. So I won't be writing down that given information. I'll just write down the problem, and then you can refer to the given information. Okay, we're going to do number 37. The parentheses aren't really necessary. You can remove them because the x minus 9 is sandwiched in between the integral symbol and the dx. Sometimes you'll see in print that they put parentheses, sometimes they don't. It doesn't matter one way or the other. Okay, first thing I'm going to do if I'm going to find this answer with given information is I'm going to look back up there at the 3 pieces of given information. Do I have any integrands that have x minus 9 in them? No, I have an integrand with x cubed, I have an integrand with x, and I have the integrand with 1. But we do know that we have a property of definite integrals that tells us I can break this apart. So looking at all the terms, there's 2 terms, I can give each of those terms, x and negative 9, its own integral and differential. Breaking this apart will help us evaluate each of these pieces individually. Well, if you look back at the top here, we do have this as a given piece of information. This is actually equal to 6. So I'm going to come down here, and I'm going to replace the value of that integral with 6. My attention turns to this integral. I don't have a piece of information given where the integrand is 9. I do where it's 1. Well, thinking about some of the properties, we can remove or pull out, if you will, a constant multiplier. No variables ever come out of an integrand. But I can put that 9 up front. And when I put that 9 up front, I'm left with just a 1 in here. Not that you have to write the 1 in. And so I've just accomplished getting something right here that was given above. So I still have 6. I have minus 9. And what's the value of this integral from above? It's 2. So 6 minus 18 is negative 12. All right, let's look at 39. All right, I'm supposed to find the value of this integral. Well, the first thing I look at is, do I have a piece of information that's given that has exactly that integrand? No, I don't. So I'm going to break this integrand apart into 3 different integrals and then use the given information above. So let's use some properties here. I think I'm going to come down here because I'll need more room. Don't forget the dx. It goes with every integral. So you can see the polynomial that was present up here, just broken apart. Okay. I don't see any exact given information above. I have to apply a few more properties. For this one right here, this definite integral, I'm going to pull that constant multiplier out front and take 1/2 of the definite integral from x equals 2 to x equals 4 of x cubed dx. Moving on here, I'm going to pull the 3 up front, because I do have this given up above. And again here, like in the previous problem, I'll pull the 2 up front, leaving 1 dx, or just dx. All right, I've got the 1/2, but I've got to multiply it by this value, which is 60. I have this integral that was given as, what was it, 6, plus 2 times the value of this integral, which was 2. And then either calculator or just do it by hand. So that's 30 minus 18 plus 4. So 34, I think that's 16. All right, ready to move on to the next group of problems. Let's look at 41. Again, we're going to be using properties of definite integrals. We're given the value of these 2 integrals, and then we're asked to complete these 4 parts based on this given information here. So it's worthwhile to kind of look and see what you're given. I'm given the definite integral of some function f from x equals 0 to x equals 5, and that's equal to 10. Notice here that the first thing I look at is, do I have the same integrand? Yes, f of x and f of x. So I'm talking about the same function here. And this definite integral picks up from where this integral left off at x equals 5. This one starts at x equals 5 and goes to x equals 7, and that value is 3. So when you look at part A, it's asking you to evaluate the definite integral from x equals 0 to x equals 7 of f of x. Well, if you added these two values together, put these two integrals together, okay, you're going to actually have this answer. So the answer for A, which is what you might have thought, is going to be 13. B, notice what's happening here with the limits of integration. I have a 5 down here and a 0 up here, but up here I had x equals 0 to x equals 5. I'm going backwards, so to speak, here. So you might remember we made an adjustment on 10 to a negative number. The answer here is going to be negative 10. Let's look at C. It asks me to evaluate the definite integral from x equals 5 to x equals 5 of this function f of x with respect to x. When your limits are the same, you're not collecting any area. There's nothing in between x equals 5 and x equals 5, so this answer is 0. Looking at D, we have a constant multiplier of 3 in the integrand. I would get that right out front, and I'd multiply 3 times the value of the integral from x equals 0 to x equals 5 of f of x. So you're ending up multiplying 3 times 10 and getting 30. I don't think I'm going to write any of that down. I think we talked through it. I hope you understood that. Otherwise, just go back and kind of listen again. Okay. All right, couple more. I want to conclude with doing a couple of the parts in problem 47. 47 is an assigned problem for you, and I'm going to do problems parts D and F with you. So on problem 47, you're given a piecewise function. It's linear, and it also has a semicircle in it. So this is a line, then it becomes a semicircle, then the function's a line and another line. We're looking at the grid from x equals negative 4 to x equals 6. Okay, because we have lines and semicircles, okay, I know that I can find the area in these regions by using known formulas. Okay, look at part D. It says find the value of the integral from x equals negative 4 to x equals 6 of this function. Well, perhaps I can talk through this. Okay, so we are actually accumulating all the value of the integral. I say area, but I need to be careful and say value of the integral. You're going to use a triangular area formula here, okay, but remember to make the answer negative because the graph of this function falls below the x-axis. So it looks like the base of this triangle would be 2 according to the scale. The height is negative 1. If you want to include that, that would probably be smart. So 2 times negative 1 is negative 2 divided by 2 is negative 1. So this region's value is negative 1. Same thing here, you might want to use the area formula for a semicircle, but don't forget to make that value negative since the graph of this semicircle falls below the x-axis. But over here, you're going to have some positive value because the graph of this function is above the x-axis. So use the area formula for a triangle, find this value, collect it with negative 1, and then collect it with this answer, which will probably be in terms of pi. No decimal answers, just leave your answer in terms of pi. Okay, let's look at part F. Part F has the sum of f of x and 2. This graph is only of f of x, not f of x plus 2. You might want to use a property to break apart this integral, like we did in some previous problems. To finish solving this right here, you already from part D have this answer, plus now to get this answer, do what we did in some previous problems where we drew a graph of y equals 2 from x equals negative 4 to x equals 6, and then that's going to create a rectangle, and then use the area formula for a rectangle to find the value of this integral, like we did on the problems back, I think, in the 20s or something. So it's just doable. It just takes some time. All right, hope this helps.